All right, so hi everybody, welcome back. What we're going to be doing today is wrapping up the chapter 15 lecture on mechanical waves. So by the end of this video, we'll be completely done with all of the content from chapter 15 that I wanted to cover. And so the next topic here is superposition of waves. Let's get into this. So we're going to start by introducing the 1D wave equation. Okay, so this is an equation that describes a wave traveling in one dimension with no dissipative forces. So remember, dissipative forces are things like friction that take away the energy of the wave and convert it to internal energy. So when we use this equation, we're assuming that there's no dissipation. We're also assuming there's no dispersion. So remember, dispersion is when different parts of the wave move at different speeds. So we're assuming there's no variation in the speed of propagation. There's just one speed, and that's it. So as long as all that is true, we can use the 1D wave equation, which is shown here. And it's a pretty simple equation. On the left side, we have the second derivative of d, that's our displacement of the wave, with respect to time, but it's a partial derivative, as we saw earlier. On the other side, we have v squared, which is just the speed of the wave squared. And again, we're assuming this is a constant. We're assuming there's no sort of variation in the speed. And that's multiplying the second derivative of our displacement with respect to x. So here we have the second derivative with respect to time, and here we have the second derivative with respect to position. So if we can solve this equation somehow, then what we'll get out of that is d of x and t. That is the displacement of our wave as a function of position and of time. So that's why the 1D wave equation is very important and useful. If you solve it, you can exactly describe what the wave you're looking at is. Okay, now if you're interested in where this equation comes from, I'm not going to show the derivation in this lecture because it's kind of long, but I'll post the derivation to Canvas so you can take a look at how we arrive at the 1D wave equation. Okay, so let's do an example. Basically, the idea here is we want to see if a given function is a solution to the 1D wave equation. So we have three functions shown here at the bottom, and for each one of them, we're going to check and determine whether or not it's a valid solution to the 1D wave equation, okay? In other words, we're going to take each one of these, plug it into the 1D wave equation, and then see if it actually works as a solution. So let's do that. Okay, so the first example is this. We're testing out the function d of x and t equals a times sine kx plus omega t. So I want to remind you that v, the speed of the wave, is equal to omega divided by k. That's something we derived in the first lecture. So therefore, I can write omega as v times k. And so if I plug that in for omega in our original expression, we have d of x and t equals a times sine. Okay, so I have an overall factor of k that I can pull out. And then I'll have x as my first term. And again, for omega, I'm replacing that with v times k, but I pulled the factor of k out, so I just have the factor of v here, and that multiplies t. Okay, so that's how we can rewrite this equation. So if I take the first derivative with respect to position, so first derivative with respect to position, what do we get? Well, I have a constant a out front. When I take the derivative of the sine function, I get cosine. And then I'll have k times x plus vt. But I need to take the derivative of what's inside the cosine function, so that gives me a factor of k out front. Now, if I want to take a second derivative with respect to position, here's what I'll get. I'll have a and k out front as constants. When I take the derivative of cosine, what I get is negative sine. And I'm just going to put dot, dot, dot because we know what's inside the sine function. But again, I pull out another factor of k because I have to take the derivative of what's inside. So instead of k, we have k squared out front. So that's the second derivative with respect to position. Now, if I take the derivative with respect to time, here's what I'll get. So again, sine goes to cosine. So I have a factor of a out front. And now this goes to cosine. Again, I'll just put dot, dot, dot because we know what's in this cosine function. But when I take the derivative of what's inside with respect to time, I'm going to pull out a factor of k and v, because k and v are both multiplying t. Okay? And then if I do it again, take the derivative with respect to time again, do the second derivative. Well, just like before, I have a times k times v out front. And cosine goes to negative sine. And if I take the derivative of what's inside the cosine function, I get another factor of k and v coming out to the front. So those will both be squared now. Okay, so the second derivative with respect to time is almost the same as the second derivative with respect to position, except I have a v squared out front, right? So this is just v squared times the second derivative with respect to position. And remember, the wave equation says that the second derivative with respect to time of our displacement is equal to v squared times the second derivative with respect to position. And that's exactly what we showed here. So yes, this is a solution to the wave equation. Okay, so basically by direct substitution, this is a valid solution. In the second example, here's what we have. We have d of x and t is equal to c times x plus vt squared. We'll do the same kind of thing as before. We'll take the derivative with respect to x. Again, this is a partial derivative. So the way I do this is I take the 2 out front. By the power rule, this becomes 2c times x plus vt to the first power. And then I have to take the derivative of what's inside with respect to x. So what's in the parentheses is just x plus vt. Again, v and t are treated as constants. So we're just taking the derivative of x, which is 1. And then if I take a second derivative, so now I'm going to have 2 times c. The 1 comes out to the front. The power of 1 comes out to the front. Then I have x plus vt to the 0 power. And then I have to take the derivative of what's inside again, but that's just 1. And by the way, when you have the 0 power, x plus vt to the 0 power, that's just 1. So this is just 2 times c, that's it. Okay, now if I take the derivative with respect to time of the function we're given, well, then I'll have 2 times c, x plus vt to the first power. And then I have to take the derivative of what's inside the parentheses with respect to time. So now x is treated as constant. V times t, that just gives me v, because the derivative of t just goes to 1. And then we take the next derivative, the second derivative with respect to time. And so here I have 2 times c, x plus vt to the 0 power. And then I have to take the derivative of what's inside with respect to time once again. And that gives us another factor of v. So now I have v squared. So the point here is the second derivative with respect to time is 2 times c times v squared. In other words, it's v squared times the second derivative with respect to position, because remember that was 2c. Okay, so this follows the wave equation also, because this follows the second derivative with respect to time is equal to v squared times the second derivative with respect to position. So this solves the wave equation. Yes, this is a solution to the wave equation. So let's try the third example, where we have d of x and t. So this is third example. D of x and t is equal to ax squared plus bt squared. Okay, so we'll take the first derivative with respect to x. Again, that means we're treating t as a constant, so we'll just concentrate on the first term. We're going to have 2 times a times x. If I take another derivative, I'm just going to have 2 times a. If I take the first derivative with respect to time, that means x is a constant now, and I'm only focusing on the second term. I'll get 2bt. And if I take another derivative, I'll just get 2b. Okay, so if we look at these two, does it follow the wave equation? Is it true that the second derivative with respect to time is equal to v squared times the second derivative with respect to position? In other words, is 2a, is 2b, which is the time derivative, equal to v squared times 2a? No. That's not true. In this case, this is not a solution to the wave equation. Okay, so the first two worked. Those are valid solutions, but this third example is not a solution. Okay, so now let's talk about general solutions to the 1D wave equation. We've talked a lot about sine waves, right? We've talked about waveforms that look like a sine curve, and that's fine. But in general, a waveform doesn't have to have that sinusoidal shape, okay? There are other possibilities. And so what we'll see is any function of x plus vt, okay? In other words, you always see x plus vt appear in this exact combination. That will describe a waveform that's moving in the minus x direction. So for example, let's say we have d of x and t is equal to a times e to the minus x plus vt squared, I should say. So if you have e to the minus something squared, the shape of that function is a bell curve, something that looks like this, and a just sets the height of the bell curve, okay? But because we have x plus vt in that function, we know that that's describing a wave traveling in the minus x direction. So again, the function itself tells us that we're dealing with a bell curve shape, and because we have x plus vt appearing in the function, that's telling us that we have this shape, this waveform, that's moving to the left in the minus x direction at some speed v, okay? Here's another example. If we have, instead of x plus vt, x minus vt in our function, then that's describing a waveform that travels in the plus x direction, okay? So let's take a look at this example. We have d of x and t equals minus c times x minus vt squared. Okay, so if you have minus some quantity squared, right? We know that looks like a parabola, a concave down parabola. That's the shape. But again, because inside of that function we have x minus vt, that's describing this parabola, this shape, that's our waveform, traveling to the right in the positive x direction, okay? So that's in general how solutions to the 1D wave equation will work. If you see x plus vt exactly in this combination, that's describing something moving in the negative x direction. If you have x minus vt in your function in that exact combination, that's describing a wave moving in the plus x direction. Okay, and in general, those are what the solutions look like. Okay, so next, we're going to talk about the principle of superposition. Now, this is a really important idea. It's going to come up time and time again throughout the semester because we'll be dealing with waves of different types. We'll be dealing with waves on strings, sound waves, light waves, and in every case that we come across, we'll be able to use this idea of superposition. So here's where the idea comes from. We have the wave equation, and this is what's called a linear differential equation. So what is a differential equation? That just means the equation has derivatives of some function. So we have like the second derivative with respect to x and the second derivative with respect to time. But we don't just have variables. We have derivatives of some kind of function. We call it linear because the equation is purely linear in terms of the function d and its derivatives. So we don't have any higher power terms like d to the third power or d squared. Everything in the equation is just taken to the first power, meaning it's linear. So when we have the second derivative here, that's just to the first power. It's not being squared or cubed or anything like that. And when we have the second derivative here, again, that's just taken to the first power. So this is a linear differential equation. Okay, so all linear differential equations follow what's called the principle of linear superposition. And here's what that means. Let's say I have two solutions to the equation, d1 and d2. So I already have solved for these two solutions. I know they're valid solutions. If that's true, then any linear combination of those is also a valid solution. So in other words, I could take 4 times d1 plus 7 times d2. Any kind of linear combination like that is a valid solution. So what does this have to do with waves? Well, again, this principle applies to the wave equation that we've been talking about throughout this video. So if we have the displacements of multiple different waves that meet at the same point in space, we can actually add those displacements together to get the total displacement, right? So if we have multiple different waves, we can add their displacements together to get the total displacement. That's the takeaway point. So this is the idea, and this is how we apply it to waves. When we have two or more waves that meet at the same position in space at the same moment in time, the total displacement of the waves is the sum of their individual displacements. So in practice, this is how we use this. Let's say we have these three waves. Let's say we have these three waves here. And what you're seeing is the displacement plotted against x. And let's say those waves all meet at the same moment in time. Well, the principle of superposition is telling me that I can simply add the displacements together to get the total displacement. So here, at x equals 0, the displacement of my first wave is 0, the displacement of my second wave is 0, and the displacement of my third wave is also 0. So the sum of those displacements should be 0. But if I look at, let's say, the peak of the first wave, that's meeting a low point of my second wave, and that's meeting kind of a trough of the third wave. So I'd have to add all of those together at this point to get the displacement, which would put me somewhere over here. And we can keep doing this for every single point, for every value of x, and when we add those waves together, that's called the superposition of the waves. When we add them together, we get this. So this is the sum of all three displacements at every single value of x. So another way we can sort of visualize this is by looking at an animation, okay? So in this animation, what I'm going to show you is two pulses that converge. So this is a pulse moving to the right. This is a pulse moving to the left. And they're moving completely separately at first, but at some point they overlap. So how do we deal with what happens when they overlap? Well, if we use the principle of linear superposition, we know that the displacements will just add together. So when they overlap, we get an even bigger peak than either one of them individually. So here's what happens when they overlap. And then they just move off separately after that. So this animation, by the way, is taken from this link here, which I'm going to just leave for you at the bottom of the slide in case you want to click on that and watch this animation later. Okay, so here's a question for you guys. We have these two pulses. This one is traveling to the right. This one is traveling to the left along a string. And they approach each other as shown in the diagram. So which diagram below shows the shape of the string when the pulses are completely overlapping? So is the string going to look like this? Answer choice A, like this. Answer choice B, like this. Answer choice C, or this. Answer choice D. So pause the video, think about it for a second, and see what you come up with. Then we'll go through it together. Okay, so we have these two pulses. One of them is shaped like this. It has a positive displacement. And the other one is shaped like this with a negative displacement. And what we're doing is looking at when the pulses overlap. So we want to sort of add those two displacements together. So what do we get as a result? Well, in this region, the displacement of both waves is equal to 0, so we'll just have a flat line there. But then here, where they start to overlap, we have a positive displacement and a negative displacement, but the positive is overall larger than the negative. So they cancel out somewhat, but not exactly. So we're still left with a positive displacement. And then, of course, once we're over here, the displacement goes back to 0. So that's answer C. That's what we get by using the superposition property when the two pulses overlap. Okay, so next I want to talk to you for a little bit about Fourier's theorem. Now, this is something that you'll have seen if you've taken differential equations. If you haven't taken that class and you've never seen this before, that's okay. We're really just going to look at this in the big picture sense. We're not really going to get into the details. So we've already seen what a sine wave moving in one dimension looks like, okay? A sine wave moving in 1D has this general form. We have d, the displacement of the wave, as a function of x and t, that's position and time, is given by a sine kx minus or plus omega t plus phi. So that's the general solution. But we already know that a waveform doesn't have to have that shape. It doesn't have to be a sine wave that looks like this. It can have other shapes to it. So if we have a waveform that does not have that simple sine wave shape, we call this a complex wave. So this is an example of a complex wave. Rather than having these nice smooth contours like the sine wave, it's jagged and it looks like this. That's a complex wave. So Fourier's theorem says that any complex wave can be described as a superposition of sine waves with different frequencies. So in other words, if I have a complex wave, I can write that wave as a sum of these sine waves that are added together. And if the sine waves have just the right frequency and just the right amplitude, I can make the complex wave by adding these together, okay? So in other words, all we really need to know about are sine waves because we can take any complex wave and understand it in terms of a sum of sine waves, okay? So let me show you an example of this. This idea that we can take any waveform and describe it as a sum of different sine waves with different frequencies. And by the way, when we take that sum, this is called a Fourier series. So here's an example for you. We have this waveform, which is called a sawtooth because it looks like the teeth on the blade of a saw. And I'm going to show you how we can take this and describe it using just sine waves that are added together. Okay, so this is the waveform, and this is what we call our Fourier approximation. So the idea behind this is, if I just have two sine waves that I'm adding together, it's not going to really look like this at all. But if I add more and more sine waves, it's going to come closer and closer to looking like this sawtooth. And if we had an infinite number of terms in the series, then we would exactly be describing the sawtooth waveform. Okay? So technically speaking, we need an infinite number of terms to exactly get this right. But as we add more and more terms, the approximation gets better and better. That's the idea. So I'm going to show you how that goes in an animation. Okay, here it is. So that's two sine waves. This is 3. Now I have 4. Now I'm picking out 5 terms in the series. Now 6. So I'm showing you adding more and more terms to the series. What starts happening is we get a better and better approximation of that sawtooth waveform. And as we keep going, we get closer and closer to that sawtooth waveform. I think I stop here at 20. Yeah, so there it is. And again, we could keep going with that, and it would be a better and better approximation of the sawtooth waveform. Okay? So I'll show you another example then. This is called a square wave. Looks like a square. And we can again model that square wave using a Fourier series with a finite number of terms. And just like before, the idea is the approximation will get better and better the more sine waves that we add to the series. So here we have 2 sine waves, now 3. And we'll keep adding more and more. And you'll see as we go on, as we keep adding more sine waves and including more terms in the Fourier series, we get a better approximation of that square wave. So we'll keep going. And I think we stop here at 18. But the idea is we could keep this going forever. And if we had an infinite number of terms, we would exactly get the square wave that we want. Okay. So all I've done so far is just show you that you can model any kind of complex wave like this if we add together a bunch of sine waves in the right combination. If you want to actually be able to calculate the Fourier series and say, well, what kind of sine waves do I need to add together to get this waveform? That's not really something I'm going to go over here. Take a course in differential equations if you want to see how that works. The point that I want to get across here, the takeaway, is that you can describe any complex wave using sine waves, which is why we're going to focus on the sine waves, really the building blocks of other types of waves. So if we can understand sine waves, we can understand any other type of wave. Brings us to the last topic in this lecture, which is standing waves. So let's get into it. Now, before I define the terms and get into any of the math, I want you to have a good picture in your mind about what a standing wave looks like. And I'm going to show you an animation here which shows how we can create a standing wave on a string. So this is a rope. It's connected to a wall at this end. And at the other end, we are free to shake it up and down. So that's what we'll do. We'll hold this end of the string, shake it up and down like this at a constant frequency. And as a result, we're going to send a sine wave towards the wall. Okay? So let's just look at the animation and see what happens. So we're sending out the sine wave. It's going towards the wall. But what happens when it reaches the wall? You're going to get a reflection. A wave reflects back off the wall this way. And now what you have are 2 different waves which we have to add together. You have the original wave that's traveling towards the wall, combining with the reflected wave that's coming back in the other direction. And when those 2 waves add together, the result of that is what we call a standing wave. So now you're looking at a wave that's not really traveling in either direction. It's just standing still and oscillating in place. Okay? So this is the standing wave that gets produced when those 2 waves traveling in opposite directions combine and form the standing wave. Okay, so a standing wave can be thought of as a superposition of 2 waves that have the same amplitude and frequency, but travel in opposite directions. Okay, so in other words, we'll have D1, which travels to the right, and we'll have D2, which travels to the left, but then D total is the sum of those two, so it's D total equals D1 plus D2. Now remember, this is how we can describe a wave traveling in the plus x direction. We have D1 equals A times sine of kx minus omega t. So this negative sign indicates that we're traveling in the plus x direction. The other wave, D2, is equal to A times sine kx plus omega t. So again, this plus sign indicates that this wave is traveling in the negative x direction. So other than that, the waves are exactly the same. They have the same exact amplitude A, and they have the same exact frequency omega. The only difference is the direction they're traveling in, which is accounted for by the sign difference in the two functions. So let's first take a look at this visually. So we have D1 and D2 shown independently. Those are the blue and the red curves. And then the black curve is the sum of those two, which again is that standing wave. And notice that the standing wave is not traveling in any particular direction. It's just oscillating there in place. That's what a standing wave really is. So what we're going to do next is work out, using a little bit of math, what happens when we add these two waves together. What kind of function do we get for D total? So let's work that out. Okay, so what we want to do is figure out what the expression for D total is. And remember, this is going to be a function of x and t. And it's the sum of D1, which is a function of x and t, plus D2, which is also a function of x and t. So both of these functions have the same constant A, amplitude out front. So I'll pull that out. And then the first function is sine kx plus omega t. And then we have sine kx minus omega t. So that's what we have to add together. So for this, I want to bring in a trig identity. You may have seen this before. Sine of, let's call it theta 1, that's just some angle, plus sine of theta 2 is equivalent to 2 times sine theta 1 plus theta 2 over 2 times cosine theta 1 minus theta 2 over 2. So here we're taking the sum of the two angles divided by 2. Here we're taking the difference of the two angles divided by 2. Now, in our case, I'll call theta 1 this guy right here, and I'll call theta 2 this guy right here. So whatever is inside of the two sine functions in our expression. So we're going to have, using the trig identity, theta 1 plus theta 2 over 2. That's going to go inside of sine. So for our purposes, that's a half times, okay, theta 1 for us is going to be kx plus omega t. Theta 2 is going to be kx minus omega t. So that's going to be a half. Omega t and minus omega t cancel, and then we get 2 times kx. But multiplied by the 1/2 factor gives us just the kx, okay? Okay, then we have theta 1 minus theta 2 over 2. So for us, that's going to be a half times, again, theta 1 is kx plus omega t minus theta 2, which is kx minus omega t. So this is going to be a half. Now this time kx cancels out here and here. And then we're going to have 2 times omega t remaining. And of course, multiplying that by a half gives us just omega t. Okay, so using the trig identity, d total as a function of x and t. So we had the factor of a out front already, but when we use the trig identity, we bring in a factor of 2. Then we have sine of theta 1 plus theta 2 over 2. That's this expression, which we saw was just kx, so I'll have sine kx here. And then we have cosine of theta 1 minus theta 2 over 2, which we just saw works out to omega t. So this is the expression for a standing wave. Okay, so here's the result. When we think of a standing wave as a superposition of two waves that have the same amplitude and the same frequency that are traveling in opposite directions, the result we get when we add those two waves together is d total of x and t is equal to 2a times sine kx times cosine omega t. So that's what the standing wave, which is not moving, looks like when we add the two oppositely traveling waves together. So let's do an example of this where we analyze the function for a standing wave. So a standing wave on a string is described by the function d of x and t is equal to 0.0135 times sine of 251x times cosine of 432t. All the quantities here are given in SI units. What is the wavelength in centimeters of this wave? What is the frequency of the wave in hertz? And what is the maximum displacement of the string at x equals 3.45 centimeters? So we'll work this out and see what we get. Okay, so we'll start by writing down the function that we're given. D of x and t is equal to 0.0135 times sine of 251x times cosine of 432t. And let's just make a direct comparison between this and the general solution that we came up with. 2a times sine kx cosine omega t. And just by making that direct comparison, we can see that k is equal to 251. Now, you might be worrying about the units at this point, but everything is in SI. So we have radians per meter. That's the SI unit for k, the wave number. And remember also that k, by definition, is 2 pi divided by lambda. So if we want lambda, if we want the wavelength, we're going to take 2 pi divided by k. So we have 2 pi radians on top. We have 251 radians per meter on the bottom, which works out to a wavelength of 0.02503. That's in meters. Now, we'll want to keep 3 sig figs on that. So therefore, this can be thought of as 2.50 centimeters. That's the wavelength. Okay, also, by direct comparison, we can see that omega is equal to 432. And again, the units, which are just not written here, are SI units of radians per second for omega. And of course, omega is equal to 2 pi f. So the frequency of this standing wave is equal to omega over 2 pi. So we have 432 radians per second divided by 2 pi radians. And what we get as a result of this is 68.75. We're left with just seconds inverse as our unit. Keeping 3 sig figs, we'll get 68.8 hertz. So again, remember, inverse seconds, hertz, that's the same unit. So 68.8 hertz is our frequency. Okay, for the last part of this, we're going to see what happens when we plug in a particular value of x. So x is equal to 3.45 centimeters. And then we'll just leave t alone. So what do we get? We have 0.0135 out front. And then we'll have sine. We're taking the sine of 251 radians per meter. And then that's K. We're multiplying by X, which is 0.0345 meters. We need the units to be consistent here. And then we just have cosine of omega t multiplying that. So in other words, at a fixed value of x, we're going to have just some constant multiplying cosine omega t. So this constant right here, if you calculate it, is going to work out to 0.009352, and the units are meters because this has the SI unit of meters out front. And then we have our cosine omega t. Okay, but the thing about cosine is it ranges between -1 and 1. So this represents the maximum displacement. The factor out front is the maximum displacement at x equals 3.45 centimeters. So D max that we're looking for is 0.009352 meters, but we'll keep 3 sig figs on that. And converting that to centimeters gives us 0.935 centimeters. So the point of this is not all parts of the string, not all parts of a standing wave have the same maximum displacement. Okay, so for the rest of this video, we're going to be talking about standing waves on strings. So the general idea is we have some kind of string, it has a length of L, and it's held down at both ends. So this is the kind of thing you would see on a guitar, or on a violin or a cello. Any kind of stringed musical instrument, this is essentially what we're dealing with. So if we use x, the x-axis, to keep track of different points along the string, at x equals 0, that will be the left end, and again the string is held down here, it's not moving here. At the other end of the string, where x is equal to L, we also hold down this end. But in between, the string is free to vibrate up and down. So what kind of wave would we have in between those 2 points, x equals 0 and x equals L? Well, we'd have to have a standing wave because there's nowhere for this wave to go. It has to be confined within that little space. So it's got to be a standing wave. Now, if we look at points on the string, we'll see that in certain places, the displacement is always equal to 0. So there are certain points along the string where the displacement is always equal to 0, and we call those nodes, okay? You'll also find at points along the string, there are some places where the displacement reaches a maximum, where the displacement is bigger than anywhere else. And that's called an antinode. So here's a node where the string just doesn't move, it doesn't have any displacement at all. And here's an antinode where the string has the maximum displacement, okay? So if we take a string like this and we pluck it to make a standing wave, we know automatically that the ends of the string are going to be nodes. In other words, x equals 0, the string is held down, so there's no displacement. It just stays in that one place. And x equals L, there's no displacement. So again, it has to stay in that one place. So at all times, we have d, the displacement, at x equals 0 is equal to 0. And the displacement at x equals L also has to be 0. So using that fact, or those 2 facts, we're going to derive what type of waves can actually be on the string. Okay, so we're going to start here and do a quick derivation. Okay, so starting with the general form of a standing wave, we have d of x and t. is equal to 2a times sine kx times cosine omega t. So this is a general standing wave. Okay, so we have a node at x equals 0. That's where the string is held down. So if we plug in 0 for x, here's what we get. We have 2a, and then we have sine of 0, and then cosine omega t. But the thing is, sine of 0 is equal to 0. So this works. That's just verifying that we have a node at x equals 0. There's no displacement. On the other hand, we have a node also at x equals L, because the string is also held down there. So now I'm going to plug in L, the length of the string for x. So we have d of L and t. So I'm going to have 2 times a times sine kl cosine omega t. But the thing is, this has to be 0. The displacement when x is equal to L has to be 0 for all times. For any time t that you plug in, we have to get 0 displacement. So what that means is this part right here, sine kl, must be 0. So what we have is sine times kl, or sine of kl, is equal to 0. Now let's think about this carefully. If sine kl is equal to 0, that means kl could be 0, right? Because sine of 0 gives you 0. It could also be pi. Sine of pi gives you 0. It could be 2 pi. Sine of 2 pi also gives you 0. 3 pi also works. I hope you see the pattern here. In order for us to have a node at x is equal to L, we need k times L to be equal to n times pi, where n is just some integer. It could be 0, 1, 2, any integer at all. And of course, k is equal to 2 pi divided by lambda. So we have 2 pi divided by lambda times L is equal to n times pi. And if you rearrange this to solve for lambda, canceling out the factors of pi, you get lambda is equal to 2L divided by n. Again, n is some integer. And we said up here that n could be 0, 1, 2, etc. But when we solve for lambda, when we solve for the wavelength, if you plug in n equals 0, you're going to get infinity out. You're going to get an infinite wavelength. That doesn't really correspond to anything physical, so we're going to leave off n equals 0 and just say n can be 1, 2, 3, and any integer after that. In other words, if we have a string that's held down at both ends, only certain wavelengths are possible. Okay, only wavelengths that fit this description of lambda is equal to 2L divided by n for an integer value of n, only those will work. Okay, so what we found here is that when it comes to a standing wave on a string, there are only certain wavelengths that are possible. Okay, in other words, you have a string that's held down at both ends. It can only support waves with a certain discrete set of wavelengths. Okay, so in other words, lambda, as we discovered, has to be equal to 2L divided by n for some integer value of n. So n can be 1, 2, 3, 4, and so on, but only those specific values of the wavelength will actually work. So let's take a look at some possibilities then. What if we set n equal to 1? Then we'll have lambda is equal to 2L. In other words, the wavelength is twice the length of the string, meaning on the length of the string, you can fit half of a wavelength, okay? So if we had a full wavelength, we would have the wave going up with a positive displacement here, and then over here with a negative displacement coming back to where you started. That would be a full wavelength. But if we have half a wavelength, it's just this part. So what we say is the string makes a single loop. That's one loop. And of course, if we were to watch this string vibrate up and down, it would vibrate up and down like this while keeping the ends of the string as nodes which are not moving. Okay, so that's what n equals 1 looks like. You have a single loop like this. Okay, if you plug in n equals 2 into this formula, that 2 on the bottom will cancel with this 2 on top, and then lambda is just exactly equal to L. So in this case, the length of the string is one wavelength. So in other words, you're fitting a full wavelength in between the ends of the string like this. And what we say is you have two loops, okay? Because this antinode is going to vibrate up and down like this. This other antinode is also going to vibrate up and down like this. And then you're going to have a node in the middle which doesn't move. So you have two loops in your string for n is equal to 2. So if n is equal to 3, then you have lambda is equal to 2/3 L, or L is equal to 3/2 times lambda. So in other words, you're fitting 3/2 of a wavelength onto the string when you set n equal to 3. So you're going to have one full wavelength here, and then half of a wavelength, and that's what fits on the string. So now you have three loops. You have an antinode here that bounces up and down, followed by a node, another antinode that bounces up and down like this, followed by another node, and then another antinode that bounces up and down like this. So you have three loops for n is equal to 3. And we could keep going with this, right? There are obviously other values of n we could do, but hopefully you get a sense of how to visualize these standing waves for different values of n. So that leads us to a question. We have a guitar string with a length L is equal to 57.8 centimeters, which is held down at both ends. Can this string sustain a standing wave that has a wavelength lambda equals 9.25 centimeters? So if the length of the string is this, can we have a standing wave whose wavelength is this? Is that possible? Just try to answer yes or no. So pause the video, try to work it out, see what you get, and then we'll go through it together. Okay, so what we worked out is that for standing waves on a string, the possible wavelengths are lambda is equal to 2L divided by n, where n is an integer. So n is 1, 2, 3, or any integer. So what I'm going to do is take the equation and solve for n. N is equal to 2L divided by lambda. And I know that n has to be an integer. So I'm going to take the length of the string that we have L and the wavelength lambda and see if it actually works out to an integer when we do this calculation. If it does, then we're fine. If it doesn't work out to an integer, then this is not a possible wavelength. So we have 2 times L. L is 57.8 centimeters. Divide by lambda, which is 9.25 centimeters. And this works out to 12.5. That's not an integer. So because this doesn't work out, this is not a possible wavelength. Okay, so we saw that for standing waves on a string, only certain wavelengths will be possible. It's also true that only certain frequencies will be possible. And the way we'll see this is, remember, we derived a relationship between the wavelength and frequency, which is v is equal to lambda times f. This says the speed of the wave v is equal to lambda, the wavelength, times the frequency, which is f. So that relationship still holds true for standing waves. So in other words, if we want to solve for the frequencies, we can do that. F is just equal to v divided by lambda, okay? So the possible frequencies are going to be determined by the possible wavelengths. So Fn is going to be equal to v divided by lambda n, where remember lambda n is equal to 2L divided by n, where n is some kind of integer. So if we plug this in here for the wavelength, what we'll get is v divided by 2L times n. So these are the possible frequencies. It has to be v divided by 2L times n, where n is equal to 1, 2, 3, or any other integer. Okay, so if you look at this formula for the possible frequencies, you'll notice that the lowest possible value we can get is just if you plug n equal to 1 into that equation. So that lowest possible frequency, where n is equal to 1, is called the fundamental frequency. We call this F1. Now, of course, there are higher frequencies that are possible. If you plug in, let's say, n equals 2, n equals 3, or anything else, and those are called the harmonics. Okay, so let's think about that real carefully. F1 is going to be what we get when we plug in n equals 1 right here. So that's just going to be v over 2L. So that's our fundamental F1, v over 2L. But Fn is generally speaking F1, which is, again, the fundamental right here, times n. So Fn is equal to F1 times n. That means the harmonics, the higher frequencies, are just some integer multiple of the fundamental frequency, because we just take the fundamental, we can multiply it by 2, we can multiply it by 3, 4, whatever the case may be. We're multiplying the fundamental by an integer to get the higher harmonics. That's how this works. So let's do an example then. Let's do an example where we calculate the frequencies of a standing wave on a string. So we have a metal guitar string that has a linear mass density of 5.76 grams per meter. It's held down at both ends so that the length of the vibrating portion is 57.8 centimeters and the tension in the string is 95.6 newtons. What is the fundamental frequency? N equals 1 in hertz. What are the frequencies of the next three harmonics? That would be n equals 2, n equals 3, and n equals 4, also in hertz. So let's work this out. Okay, first, we're going to remember that the fundamental frequency is given by v over 2L. And we'll remember that for a wave on a string, the speed, v, is equal to ft, the force of tension divided by mu, the linear mass density under the square root. So the speed of the waves on this string is going to be given by v. Okay, so the force of tension is 95.6 newtons, but remember a newton is a kilogram times a meter per second squared. The linear mass density is 5.76 grams per meter. If we want to convert that to kilograms per meter, we'd have to multiply by 10 to the minus 3. So kilograms per meter is now the unit. And if you solve for v, what you're going to get is 128.8. Kilograms cancel out, and we're left with meters per second as our unit, but we'll remind ourselves that we're keeping 3 sig figs on that. Okay, so what's the fundamental frequency then? That's F1. Well, that's going to be the speed we just calculated, which is 128.8 meters per second, and then we're going to divide by 2 times the length, which is 57.8 centimeters or 0.578 meters. If you work this out, you'll get 111.4 hertz, which will round to 111 hertz. So about the units here, we're left with seconds inverse after canceling units of meters, and that's the same as hertz. So, okay, the fundamental frequency is 111 hertz. But now that we know the fundamental, getting the harmonics is super easy, because remember, Fn is equal to F1 times n, where n is equal to 1, 2, 3, any integer. So we already have F1. F2 is going to be F1, which is 111 hertz, times 2, which would give us 222 hertz. And then F3 would be 111 times 3. That would give us 333 hertz. And then F4 would be 444 hertz. So these would be the next 3 harmonics above the fundamental frequency. Again, they're all integer multiples of the fundamental frequency. Okay, so one thing that you'll know if you've ever played guitar before is that you can use the tuning knobs to adjust the tuning of the guitar. So if you turn the knob one way, you'll increase the tension in the string, and when you play the string, you'll get a higher pitched sound than before. And then if you turn the knob the other way, you'll decrease the tension in the string, and you'll get a lower pitched sound than before. That's really what this question is all about. So consider the metal guitar string from the previous problem with a linear mass density of 5.76 grams per meter and a length of 57.8 centimeters. If you wanted to tune this string so that the fundamental frequency is now 82.4 hertz, what should you set the tension to? So pause the video, try to work this out, and see if you can get the answer. Okay, so the fundamental frequency, F1, is given by V over 2L, where V is the square root of the tension force divided by the linear mass density mu, and then we'll divide that again by 2L. So I want to solve for the tension. So first, I'm going to put 2L on the other side of the equation. So we have Ft over mu under the square root is equal to F1 times 2L. So if we want to get rid of the square root, square both sides. And we have Ft divided by mu is equal to 4 times L squared times F1 squared. So the force of tension, Ft, is going to be 4 times mu times L squared times F1 squared. Okay, so here's what we get. We have 4. The linear mass density is 5.76 grams per meter, but multiply by 10 to the minus 3 to make this kilograms per meter. The length is 57.8 centimeters, but in meters, that's 0.578 meters. Square that. And then the frequency we want is 82.4 hertz, which is the same as inverse seconds, and we'll square that as well. Okay, so what we're left with is 52.26 when you crunch the numbers. And then unit-wise, we have kilograms on top. We have a factor of meters on top because we have meters squared here on top and meters on the bottom. And then we have seconds squared on the bottom from the frequency over here. So a kilogram times a meter per second squared is a Newton. And rounding this off to 3 sig figs gives us 52.3 newtons. So remember, before we had F1 equals 111 hertz, and the tension was 95.6 newtons. So what we just did is we reduced the tension to lower the frequency. And again, if you've played guitar, you know intuitively that's how it works. You reduce the tension and you get a lower frequency. Okay, so we figured out that when it comes to a standing wave on a string, only certain wavelengths will be possible, and also only certain frequencies are going to be possible. But that leads us directly to the question, if you actually play the string, if you pluck a guitar string, what frequency is going to ring out? What frequency do you actually get? So the answer is, when you pluck a guitar string, you get a superposition. You get a combination of the fundamental frequency and the higher harmonics. You get a big mix of all of those different frequencies all at the same time. And the exact mixture of frequencies that you get, it depends on a lot of different things, like what are the physical characteristics of your instrument and how are you playing it? Okay, so the exact mix you get depends on some details. And this is a really good thing for us from a musical perspective, because if I played a guitar and the only frequency you heard was the fundamental and nothing else, that would sound really dull. A single frequency all by itself sounds very dull. But when you have a mixture of frequencies in different combinations, that's what gives every instrument its own unique sound. And that's how you can subtly change the sound by playing the instrument differently. So the last thing to say about this is that when we have a mix of frequencies that have an integer relationship to the fundamental, so like we saw in the previous example, you have a fundamental of 111 hertz, and then you have 222 hertz, and then 333. If they're all related by integers like that, it sounds musical when they're all played together. It sounds like a musical note. But if you were to play a bunch of frequencies that are totally unrelated to each other, just a random mix of frequencies that are totally unrelated, that doesn't sound like a musical note. It sounds completely atonal to us. It sounds like static. So that's what makes things musical, okay? We have a mixture of frequencies and they have an integer relationship to each other. That's what sounds like a musical note to us, okay? Okay, so I thought that I would demonstrate some of these ideas using an actual guitar. So I've tuned this guitar so the lowest string is D, so that's the note D. But depending on how I actually pluck the string, I can get different sounds out of that. So here's an example. Let's say I pluck the string using my thumb, kind of in the middle of the guitar string like this. So just take note of how that sounds. But if I use a sharp pick and pluck it really close to the end where it's held down here, that's the sound I get. So it sounds very different, right? And the reason for that is when I pluck it here in the middle with my thumb, I'm getting the fundamental frequency and not that much of the higher frequencies in the harmonics. But when I pluck at the end, I'm getting a lot more of those high frequencies in the harmonics. So it sounds higher pitched, it sounds kind of twangy, is what you'd say. Also, one thing you can do with a guitar is you can block out some of the frequencies. So for example, if I take my finger and I place it right here, and I'm not actually going to press down on the string, I'm just putting it here so that at that point, I'm not allowing the string to vibrate. In other words, I'm creating a node right here. So then if I pluck the string, I'm actually missing the fundamental frequency. That lowest frequency is not there anymore because I've blocked it out. I've created a node there, so that fundamental frequency can't actually vibrate. It can't actually ring out. And you can do this at different places on the guitar. Like if I do the same thing at this fret, or at this fret, I'm basically blocking out certain frequencies and only allowing certain harmonics to ring out. So the point of showing you all this is that when it comes to an actual musical instrument, there's a lot more to say about the physics than what we've done in this lecture, okay? What really gives every instrument its own unique sound and character is the mix of frequencies that you're getting. So what we've done in this class is really just talk about what frequencies are possible, what could actually ring out on the string. If you want to look into more detail about what the exact mix of frequencies you'll get is, you'll need to take differential equations and learn a little bit more about Fourier series, Fourier analysis. So the last thing I'll show you is, of course, we have the tuning knobs, and these adjust the tension of the string. So if I pluck the string here, and then reduce the tension, I get a lower fundamental frequency, and then all of the harmonics go down along with that. Okay, if I increase the tension, I get higher frequencies. That's the idea. So I think that's all I wanted to say about this, and that's where this lecture will end. As usual, we have practice problems at the end of the lecture, so do those for extra practice, especially as you study for the test. And with that said, that's the end of the video, but I'll see you in the next one. Take care.